everyone. So today we are going to learn about deformation in AS level. Now let's suppose that we have a spring with a certain length L, alright, and then we apply a force that extends the spring, and the new length it has is now LF, alright. Now, to know what is extension, extension would be the same as the change in length, and that would be, let's call it x. Now, similarly, it can also be done by, let's suppose if this spring has a length L and then you apply a force inwards which compresses the string. So now the new length would be LF, and the change in length that we call extension is going to be x, which is this. Now to bring a change in length, we have two forces which are involved, and those two forces can either be tensile or compressive. Now, tensile forces, basically, in a very simple manner, we can define that they pull the material outward, and compressive, they push or press the material inward. Now, to actually to find the change in length, which we are calling x, it's easy that we just subtract the final length minus the initial length. Now remember, if it is tension, which is pulling it outward, means it's extending and not compressing, so the answer for this would be always positive. Whereas in this case, if we find the final minus, find the extension, and that's the length final minus initial, so you would always get a negative answer. So basically what I do is I just know from this that here, since the answer to my extension is negative, so obviously the change in length has decreased, which means it is compressive. And the change in length in this dimension is positive, which means the force that was applied here was tension and is tensile. Alright, so I hope it's pretty clear, but then we can also, further see this as Hooke did, and he presented us with a law, and that's fairly simple to understand. So basically what he said was that, let's suppose if this is a string or a spring and you're pulling with a force F and it looked like, originally it looked like something this, and there was an extension X. Now if you pull the string with some force, let's suppose it's 2F, so it will show a bigger extension, alright, like it will start from here, from the original length, and it will show this extension plus this extension, which means the extension has been increased. Now you can keep on doing that until there is a point where it reaches its limit of proportionality. Alright, now we are going to explain this and see what it really means. So let's just write the law, because most of the time you will be required to write the law. Now, Hooke's law says that the force applied, whether it's tensile or compressive, is directly proportional to extension unless limit of proportionality has not reached. Alright. Okay, so now what we need to understand is that this can be demonstrated using a graph, right? And if I make a graph, so what you need to understand is that the extension is on y-axis, and let's suppose the force is on x-axis. Now, if it is written anywhere that something is directly proportional, so you must remember that if something is directly proportional, it means it will start from the origin, which is the point 0, 0 on the graph. Alright, so this is your origin, that's 0 and 0. So that's where the graph should start every single time. If it's just written proportional, it doesn't have to start from 0. So you have to be very, very mindful of that. Now it makes sense, because if you're putting extension at one end and force at another end, and the force is causing extension, so it makes sense that when there is no force, there will be no extension, right? So this is how you should always be looking at things. Now, when you make a straight line, it means it is proportional. Yes, we understand that. But then it's written unless limit of proportionality has not reached. What do I mean by that? Meaning by that is that when you extend the spring to a point where now it starts to curve, the your your graph starts to curve. At that point, the material stops following Hooke's law, because now it's not directly proportional, or it's not even proportional. So this is the point we call as limit of proportionality, which means that at this point the Hooke's law will, after this point, the Hooke's law is not going to be followed, right? Now, remember that I just put x on this axis and force on this axis. So, because generally the convention is that the independent value, alright, has to be on the x-axis, and when we call something independent, it means we can change it by, or the value is in our control, because now the force we're putting in, so that's in our control. But then the extension, alright, is actually dependent in this whole scenario, so obviously we can put it on the y-axis. But a lot of books will show you a different diagram, alright, or a different graph, or what would they do is the graph would be something like this. Now they will be showing f on y-axis and x on x-axis, so it's totally fine, because the graph dynamics doesn't change. What I mean is, then the graph after the limit of proportionality is going to curve towards x. So you must understand the graph always curves towards x, which means after limit of proportionality has crossed, the material, whether it's a spring or anything else, will actually try to extend more for without lifting a lot of load. Alright, so now this is how it is explained. Now, if you further go into it, so we must understand that if we have two different systems, or let's suppose two different springs. So what difference does they make? Alright, now see, if we want to know that how stiff a spring is, we have to look at the value of its spring constant. Alright, so basically spring constant is actually the stiffness of a spring. Now, how do we calculate it? It's quite simple. Now, stiffness can be easily calculated by taking the gradient of the f and x graph. Like, if I take two values from here, alright, let's suppose that's x1, and then if I get like x2, and then corresponding to it it's f2 and f1. So the change in f and the change in x is going to give me the value of k, which is known as the spring constant, right? And the spring constant is basically the stiffness of the spring. Now generally what we mean by stiffness is that how much of load something can bear or lift, if, alright, with showing a little extension as possible, right? Now remember, if the graph axes are changed, so this formula is quite there. If the graph axis change and here you are finding the gradient of x and f graph, so then it will be change in x over change in f. Then remember, this value, if you write it like this, it's change in x over change in f. Then this is not going to give you the stiffness, but actually the inverse of stiffness, or it's k 1 over k. So you have to be very mindful of that when you're looking at two different graphs. The graph should always be f and x, or even if it's x and f, you should understand that the stiffness is given by the change in f and change in x. So this is like a permanent formula. Other than that, I'm really sorry. Now, I will just make you understand using two graphs. So what do I really mean? And that is by, let's suppose if I make two graphs like these, alright, like these, okay. Now, you see, if there are two ways, like let's suppose there's one spring that shows a graph like this, and let's suppose the limit of proportionality has not crossed or has not reached. So the other spring shows something like that, and then on the other graph, if I tend to draw it, so the other graph is showing you similarly like that, and something like that. Alright, so how do we know which spring is stiff and which spring is not, right? So let's suppose if this is spring K1 with a stiffness K1, and this is spring that is stiffness K2 in the same graph, this is K1 and this is K2. We're looking at F and X graphs, right? So let's suppose for equal force, alright, for an equal force, alright, for an equal force, how different the extension would be for the both springs, right? So let's suppose if we're looking for any particular value, let's look at the value here, F naught. So here for this spring, the extension is going to be something like this much, right? Now, and for this spring with the same force on it, the extension is going to be something like this. So what we learned is that actually, since K1 is a greater value, which means it has a bigger gradient. So for same amount of load lifted by both of the springs, the extension here is actually equal, or the extension here is different. So it's K1, which has a greater K, the spring one, which has a greater K, is actually lifting the same load and showing less extension, so it means it's more stiff. Whereas K2, which has smaller K, right? So we can see for the same load, the extension that is being caused here is actually bigger than K2. So we can say that actually the stiffness of K1 is much greater than the stiffness of K2. So also you can find it using the obviously the gradient, and then when you find it using the gradient, you can actually understand from it. Now for the other graph, we can actually check if for an equal extension, alright, for an equal extension, how do these two springs behave. So let's suppose if we want an extension of x from both of the springs, so let's see how much load would they lift. Alright, for this much extension, K2 is going to just lift a force F, right? Let's call this F1. And then for the same extension, to bring it in K1, you need a bigger force, that's 2. So you see, what we must understand is that since K is more stiff, right, and K2 is less stiff, so actually for the same extension to show in K2, you need a very small force. So even if you press it or stretch it, so with a small force, the same extension is going to come. But for K1, for the same extension, if you want a same extension, so you have to apply a bigger force, since basically it's a stiffer spring, so you need to have a larger force in order to extend it. So similarly, like this proves that K1 has greater K2. That means that actually the force that is being applied on it, okay, has to be this force, let's call this force 2. The force 2 has to be greater than force 1. Now, so this brings us to an idea that we can relate force and extension, and when we do so, we have to we remove the proportionality sign, so we have to apply a constant, and that is K. So we get a formula, and that is force is equal to the spring constant times the extension caused by the force, and that's what the Hooke's law told us in the first place. Alright. Okay, now what we must understand in the next part, that what if we have a combination of springs that can change the dynamics of question, but they're frankly very easy. So now looking at these two graphs, right, we are going to take help from there and explain. So we have two types of questions that may come in your exam. So the questions might have a combination of series, a combination of springs that are in series, and a combination of springs which are in parallel. Now how do we understand this? It's quite simple. Let's suppose we have one spring, alright, that's here, and another spring that's here, is like suspended like this, and then we have a load L which is on them, right? Now what you must understand is that whenever this is going to happen, the force that is actually, let's suppose that this is the gravitational force that's there, the force or the load is not going to be divided among them, but in fact it's just like a train, that the force that this spring feels will be, let's call F1, and the force that this spring is going to feel is, let's suppose, F2. So the force is being translated in both of them in a straight, line of action, which means that the force F1 will be equal to the force F2. Alright, now let's say that this spring has a stiffness of K1 and this spring has stiffness of K2, right? So, like we did, that for an equal force, we must understand that the stiffnesses for two different springs having different stiffnesses, the extension is going to be different, which means that for K1, the extension is going to be x1 and the extension for this is going to be x2. Now if you want to know what is the total extension in the system, we can say the total extension is x, and then it's given by the sum of both extensions, the individual extensions of the springs, right? Now since we have this and we know the formula, and that is that connects k with f and x, and that's f is equal to kx. So what I can do is I can really put, I can change this formula like I can write it as x is equal to force times k. So I just divided k, and then I use these values, alright, and substitute these values in this equation. Now if I substitute it, so x obviously is equal to f over k, then x1 is equal to f1 over k1, then similarly f2 will be equal to f2 over k2, and so on, right? It does not matter if it's one spring or two spring, it could be many. Now since I initially demonstrated, or I just claimed that since it's like the springs are the same line of action, the forces are not going to divide amongst them. In fact, it's going to be the same in all the springs. So the forces can be cancelled out. So then we get a formula, and that formula is 1 over k is equal to 1 over k1 plus 1 over k2, and so on. So what we got is, we got a relationship between the k's and the stiffnesses of both springs, that we can add the inverse of springs and get the inverse of the total k that this system has now achieved, the stiffness this system has now achieved, and now then we can find k to get our values simply, right? Now similarly, like parallel, we can also make a combination of parallel, and let's suppose this is one spring and the other spring is this. Both springs have different value of k. Let's call this k1, let's call this k2, and it is connected with a board with a force that is like a constant force F, right? Now let's suppose that the extension that we are trying to bring the board like exactly horizontally downwards. So then the extension that we be witnessing, like this extension in x1, let's call this the extension x2 in this, and let's call the extension x1 here. So actually the total extension is going to be the same if I'm again saying, if we are trying to bring the board downwards horizontally, right? Now, so we have same extension, but now the difference would be that if we are looking for the same extension, we must understand that for same extension, both the springs would actually have different forces on them, right? So now we can apply these forces, and from that we can understand, like for example in this spring, let's call this the force was F2, and then this spring the force was F1. So the total force then would be F1 plus F2. So in parallel, the forces tend to divide, the springs tend to divide the forces among them, and then we can easily see if this is a stiffer spring, obviously it's going to take a bigger force, and if it's a less stiff spring, it's going to take less force, that we already discussed in the earlier part. Also, you can refer back to this um, diagram of the two springs made on the graph right now. Now, since we know that F is equal to kx, so this value can be substituted in this equation, and then it would be kx is equal to k1 x1 plus k2 x2. Now we should understand that we are bringing, or we're trying to have the same extension in both of the springs, so we can cancel out the extensions, and then we get a simple concept, and that is that the spring constants of all the springs that are in parallel can be added together to give you the combined, or the combined spring constant for the system, right? Not an individual spring. So this is how we can find the the relationship between three equations that we just drew. Now, most of the time, alright, in your questions, the spring constants are going to be the same, but sometimes the spring constants may be different. Now, if there is no requirement for a spring to show the same extension, like if this is a different system altogether, and most of you might be thinking that what if we just have two springs, and let's suppose this is K1, this is K2, and this time you're not actually applying a force, you're just suspending the board in gravity, right? What will happen if K2 is more stiff than K1? So basically nothing is going to happen except for the fact that the board is going to tilt like this, since K1 is going to extend more than K2, alright, because there's no load, or you're not trying to lift it. So how would we find this extension? And it's fairly simple, because if it does not extend at all, which is not a possibility at all, so if you look at the diagram, it would be something like a trapezium, right? What do I mean by trapezium is that is the initial position, alright, that is the extension of spring 2, that is the extension of spring 1, and then we can subdivide it into different regions, find the angle, and do the calculation, alright. Since this angle, this part is going to be x2, so we can relate the equations, but it's quite rare that this kind of question is going to come, but you should be knowing it, right? Now, the same principle, alright, the same principle can be applied for different materials. Like sometimes we are going to do it like in as we progress into the chapter, we're going to do it. But then sometimes they might even give you two materials, right? And those materials might be, let's suppose if this is steel and this is copper, and they're saying, alright, we are applying a force here, how would they extend differently? So the rules are same, alright, but this time, since for material it has thickness something, so we actually go into Young modulus, so we are going to discuss this there. Now, going back to the whole thing, alright, so let me just quickly give you a quick revision before we start doing the questions, so you don't have to rewind the video. So first of all, I told you that whenever there is a positive extension, when you apply force on it outward, that's called tensile force, and when there is negative extension where you compress the material, so basically that's a compressive force. Now Hooke's law told you that the force is actually directly proportional to the extension caused, unless limit of proportionality has not reached. And limit proportionality is the point where a material starts to curve and it stops following Hooke's law. Now, you could actually find a stiffness of a spring by finding the change in force over the change in extension cos, and this factor is given by K, which is a spring constant, and it gives you the stiffness of the spring. Now, further we actually concluded that for the same force, if there is two springs, um, the force that if we have to apply the same force, how the two things are going to extend, and that shows us that for the same force, X is going to be, for a bigger stiffness, it will show less extension, and for smaller stiffness, it's going to show more extension. But then, if we want them to, go down or have the same extension, then F1 and F2 will have different forces applied to them because they have different spring constants. And then we did the combination of springs where we learned that in series the forces remain the same and extensions are different if there are different spring constants, whereas the k is given by 1 over k is equal to 1 over k1 plus 1 over k2. Now, for a parallel combination, if we are actually trying to pull both strings together, so the force on both the strings will depend on how stiff that is. Stiffer spring will have more force, and less stiff spring is going to have less force on it. And of course, the equations are such that the force is divided amongst the springs, so they add up. Whereas the k, alright, is also added up like just addition. Alright, now we are going to back. Let's go and check a few questions from exam perspective, and here we are. So this is the first question that came in November 14. That's paper 1-3. Alright, so let's see whether it's the same. Now, it says two springs, one with spring constant 4 kilonewton meter and the other with spring constant 2 kilonewton meter are connected as shown. Alright, and the load is something like that. What is the total extension of the spring supporting 80 newtons? So we know that the force here is actually 80, and the first thing we should understand is that the both springs are in series. So yeah, so force in this spring, alright, and the force in this spring are both going to be the same, alright, 80 Newton and 80 Newton. Now, we have two ways if we have to, go with the flow. So they're asking total extension of the springs, right? So they're asking about the system. So one, by following the equations, right? And the equation says that we could use the whole thing, like we want to find the k, so it can be 1 over k for the combined k of both springs, and 1 over k1 plus 1 over k2. Now, if you notice, it's given in kilo and kilo, so let's just keep it in kilo and then change afterwards. So it's going to be 1 over 4 plus 1 over 2. So then we take the LCM. Alright, I don't have the calculator, so I'm trying. Alright, it's 4, and it's going to be 1 plus 2, and then is equal to 1 over k. So this comes out to be as 3 over 4, and then k would be 4 over 3 Newton, alright, kilo Newton per meter. Alright, kilonewton per meter. Alright, so this is the equation for us. Now, we can find the total extension by applying the formula F is equal to kx, and then k would be, alright, so it's kilo, so it will be 4,000. I'm multiplying 4 with 1,000, and then 3 times x is what we need to find. That will be the total extension in the system, and the force is 80. Alright. Oh. Alright, now. So it's going to be 80 times 3 divided by 4000, and then 0 cancels 0. Alright, 4 ones are and 4 twos are. So we get 2 3s are 6 over 100, that's x. Now we can find it like 0.06, that's in meters because everything we took in meters and the answer is in centimeters. So now we can change that, and if we change it to centimeter, we have to multiply by 100, which means it will be 6 centimeter, and that's what our answer is. Let's see. Now there's another way to do it, like obviously I just made a mess because I don't have a calculator with me right now and I really don't want to pause the video. So what I could do is I could find the extension in both the springs individually. Since I know that the extension in a series combination are like added up together, the total extension. So I could find for the first one, that would be like f is equal to kx, then f is 80 for the first one. Let's suppose the k is 4, that's 4 kilo Newton meters, so 4 into 10 raised to the power 3 times x, right? So I can find x here for the first spring, and then I could do the same for the second spring, and then whatever the values are, we can just add them together, and and we have the same answer. So it really depends if you want to use this equation or if you want to just use this equation. It's up to you. Now, why do you think this equation is handy? If there are a lot of springs, like there are 3 or 4 springs which are in series, so it gets like, by making equations again and again, it gets really long. So we could always find a combined k and then a combined force and then find the combined extension. That would be my goal. Now let's do the next part. Alright, so a number of identical springs. So it means if it's written identical springs, it means all of them here have the same stiffness. Alright, a spring is known for its stiffness. Alright, all of them have the same stiffness. Okay, and join in 4 arrangements. A different load is applied to each arrangement. Which arrangement has the largest extension? So he's looking for the largest extension in this arrangement. Alright, we could do that. It's not that hard. Alright, so these type of questions, alright, generally have they are quite long to do if you try to solve them. So usually I try to pick the best ones. Alright, let's see. Okay, so I am a bit, I know in a series combination the force is not divided, in fact the force is applied. So here there's the 3 springs with 1 Newton force on all of them, and like we said, here the 2 Newton force on all of them, but here the forces are divided. Like obviously if they're equal, they're both the same spring, so we must understand that 3 Newton is going to apply on it and 3 Newton is going to apply on it. Alright, so it'll be lifting like that, and in here I think it's 8, so 8 by 3 on it and 8 by 3 on it and 8 by 3 on it as well. Now for the same spring constant we can find here 2 and 2. So let's see. So here because series, so we can see if what happens to spring constant. So for A, alright, I'm going to do it. Now for A, it's going to 1 over k is equal to 1 over k plus 1 over k. Why? Because they have the same. Alright, this is the combined. So this is going to be k and then k 2k, and then the combined k is going to be k by 2, right? So I can find the extension here, and then the extension would be f is equal to kx, and then this is 2, this is k by 2, and this is x. So actually the extension would be 4 by k is equal to x. Alright, now since they all have the same k, to make things simpler, I can take k as 1 Newton per meter. So we can say, alright, x will have 4 meters of extension. Oops, that's large. Okay, now for the next one, we could do the same, and then it would be for b, it would be 1 over kc, the combined, over 1 over k plus 1 over k plus 1 over k. So theoretically it's 3, and now it's 1 over kc, so the combined would be k by 3. Now if you use the same formula, and here it would be f is equal to kx, but the force is 1 this time, and this is going to be k over 3 times x. So actually if k is 1, which I suppose, alright, so then basically the extension will be 3 meters. Alright, so this is not a part, right? Here the force is 3 newtons, right? And here what we needed to understand was that 3 newtons on k. Alright, that seems, a big extension. So let's see if this may be the answer. So for part C, what we could do is, since k's add up together, so k will be k1 plus k2, that is 2k, since both are the same. So now we can apply f is equal to kx, and then f was actually 6, k was 2k times x. When you divide it, so 2 divided by 3, it's 3, k is 1, so x is this, so this is not a part, so this is still winning, alright. And then if it is divided by 3 and it's 8, so 8 divided by 3 is actually something I believe is lesser than 3 newtons, right? It's less than some value which is less than 3 newtons, right? Whatever it is. So what we must understand is that if 3 newtons in parallel, alright, could not bring an extension more than this one, then how less than 3 newtons would bring the extension? This can't be the answer. So the only answer is A. Alright, so it did get me to work a bit, but as you go on, you need to understand this, that usually first I always check the series ones, so they will have obviously a greater chance of showing greater extension, because in series the forces remain the same. Alright, now this question, the next question is a bit difficult and says, to determine the mass of food in a pan, the scale is used for high sensitivity for small masses but low sensitivity for large masses. Okay. To do this, 2 springs are used, each in different spring constant k. One spring has low spring constant, other has. Alright, okay, now which arrangement is suitable? So what we are looking for here is basically determine the food, the scale used for. The scale is used as high sensitivity for small masses, alright, and low sensitivity for large masses. It means for low sensitivity, which means even if it's a large mass, so k can be bigger. So obviously the k for something we don't really need, like don't need to be sensitive, so it shows little extension for the high load. So basically a high k can work for it, and for low sensitivity obviously a low k can work for it, because even if small change in force can occur, it should show extension. So now okay, if we use this system, which is this, so it might just work. But the fact is, if you put a lot of load on it, so it's going to bear this, but this is not going to bear it. And then maybe it's like it will extend a lot, which will again show a different value. So I don't think it's appropriate, since uh, it will be like something like that. Alright. And then this is low K and this is high K. So I think this is not proper, because if you put a lot of load, it might just cross its limit of proportionality and give you wrong values. So no. Here parallel, no, because it's going to give you the wrong reading, because even if you put a small load, it's going to be something like that, and then it would not be appropriate at all, because it will extend more. So how would you take the readings? Because some of the readings will, some of the forces are going to be divided, so we can't take parallel at all. Now here in part A and C, so rigid box, alright. So already high K is not going to extend, so we don't really need a rigid box to support it, which means this can't be the answer. The only answer can be correct is A, because you see, if you put a small load, alright, the spring will show you extension, right, like it's showing right now, and a little extension can be sensitive for small loads. But if you put a high load or a big load, so this is going to extend, alright, but this is going to be restricted by the rigid box, which means the readings would be actually quite appropriate, since in series the loads are just transferred to one another. So box is going to lift it up, save this, and this guy is going to tell us the right one. So yeah, it's A. I hope you understand how parallel and series combinations are dealt with in certain questions. Alright, so you don't really have to worry about it. All you need to do is keep your mind focused on two things, and that is, one, series, the forces in series, the forces are the same. In parallel, the forces divide. Alright, once you do understand that concept, there's no question that's harder or easier for you. Alright, they will always be, you'll be master of them. Alright, so see you in the next video, and please subscribe and like and share. Alright, okay, good luck.